Does water memory exist? Water memory is the idea that water can remember substances once dissolved in it, even after they are diluted to the point where no molecules of the original substance remain. This concept challenges traditional chemistry, which states that water's properties depend on the concentration of its components. Proponents suggest that water's unique hydrogen bonding network allows it to form temporary structures or patterns influenced by the solute, which might persist even after dilution. For example, in homeopathy, water is believed to retain the essence of a substance, producing therapeutic effects despite extreme dilution. While experiments continue, skeptics argue that water's constant molecular motion should erase any memory, and so far, no consistent evidence has been found. As we wrap up our exploration, it's clear that the debate around water memory is far from over. While some researchers remain hopeful, others call for more rigorous evidence. The quest for understanding continues.
Introduction to water memory. Water memory refers to the hypothesis that water retains information about substances that were once dissolved in it, even after dilution to the point where no molecules of the original substance remain. This concept directly challenges the principles of molecular chemistry, which assert that the properties of a solution are determined by the concentration of its components. Advocates argue that water's unique hydrogen bonding networks allow it to store structural or energetic imprints of solute interactions. Some claim that these imprints influence biological systems, providing a mechanism for homeopathy's effects. Water is known to exhibit anomalous properties, such as its high surface tension and density anomaly, attributed to its hydrogen bonding network. Proponents suggest that these anomalies may extend to the ability of water to form persistent, solute-specific configurations, even after extreme dilutions. Homeopathic remedies rely on water memory, claiming therapeutic effects from solutions so diluted that no molecules of the active substance remain. Water memory is like a recording device that captures the song of a substance even after the instrument is removed. Molecular structure of water, inspiration for the theory. Water molecules form intricate hydrogen bonding networks that constantly break and reform within femtoseconds. These dynamic interactions create clusters of water molecules that might transiently encode information about dissolved substances. While the lifetime of individual hydrogen bonds is short, proponents of water memory suggest that solute interactions could induce longer-lasting structural rearrangements, potentially acting as a molecular memory. Experimental techniques like X-ray scattering and neutron diffraction have revealed that water's hydrogen bonds can form ordered networks around solutes. These networks could theoretically persist after the solutes are removed, though skeptics argue this contradicts the high mobility of water molecules. Studies on water clustering have shown that even trace amounts of solutes can induce structural changes in water that outlast the presence of the solute itself. Water's molecular clusters are like fleeting sandcastles built on a beach, but proponents argue that some structures remain etched in the sand longer than expected. The concept of water memory gained attention in the scientific community through Jacques Benveniste's 1988 study in Nature. He reported that water exposed to antibodies retained their biological activity even after extreme dilutions. Critics noted a lack of reproducibility and claimed the results could be attributed to experimental error, contamination, or even placebo effects. The study was followed by skepticism, with many dismissing water memory as pseudoscience. However, ongoing research continues to test its validity. One proposed mechanism for water memory involves quantum coherence or electromagnetic fields, suggesting that water could behave as a quantum system under certain conditions. Critics argue that such effects would require extraordinary experimental precision, which has not been demonstrated. Subsequent attempts to replicate Benveniste's results under double-blind conditions consistently failed, fueling skepticism about water memory's scientific basis. The controversy surrounding water memory is like trying to prove a ghost's existence. Compelling anecdotes abound, but scientific evidence remains elusive. This analogy highlights the difficulty in validating water memory through empirical research. Advanced analytical techniques, such as nuclear magnetic resonance, NMR, dynamic light scattering, and Raman spectroscopy, have been employed to study water memory. Some researchers claim to observe persistent structural changes in water after exposure to solutes, even at high dilutions. These findings are highly contested, as skeptics argue that such changes are more likely due to contamination or measurement artifacts rather than genuine memory effects. Critics point out that water is a highly dynamic system, and any observed memory effects could arise from impurities, dissolved gases, or the experimental apparatus itself. Proponents argue that these possibilities have been ruled out in well-controlled studies. In one experiment, water exposed to electromagnetic frequencies associated with a solute exhibited changes in NMR signals, hinting at structural alterations. Modern experiments on water memory are like trying to capture a shadow with a camera. Sometimes you think you've succeeded, but others question whether it was really there. This reflects the ongoing debate about the existence of water memory. Some theories suggest that electromagnetic fields generated during solute interactions may imprint information onto water molecules. These fields could hypothetically induce rearrangements in water's hydrogen bonding network, creating persistent patterns that represent the solute. Critics, however, argue that the thermal motion of water molecules would rapidly erase such imprints. Quantum field theories have been invoked, proposing that water's molecular vibrations might resonate with electromagnetic frequencies associated with specific solutes, preserving a memory of their presence. These ideas remain speculative and are not widely accepted by the scientific community. Experiments have demonstrated that exposing water to specific electromagnetic frequencies can alter its surface tension, but it is unclear whether these effects persist after the field is removed. Electromagnetic fields shaping water's memory are like invisible hands sculpting a fluid into intricate shapes, illustrating the potential complexity of such interactions. If water memory exists, it could profoundly impact biology and medicine. Highly diluted solutions might retain therapeutic properties, offering a novel drug delivery mechanism without active ingredients. This challenges the dose-response relationship fundamental to pharmacology, where efficacy is traditionally linked to the concentration of active molecules. In biological systems, water plays a critical role in protein folding, enzymatic activity, and cellular communication. If water memory influences these processes, it could provide new insights. It could provide insights into phenomena like cellular signaling and hydration-dependent metabolic changes, enhancing our understanding of biological systems. In one study, water allegedly memorized DNA sequences and transmitted the information to distant biological systems, though these claims remain unverified by the scientific community. Water with memory in medicine is like a shadow of a key that can still unlock a door, symbolizing how diluted solutions might retain therapeutic effects despite lacking active ingredients. The primary challenge to water memory is its incompatibility with established scientific principles. The high kinetic energy of water molecules means that any structural imprints should dissipate rapidly. Additionally, the lack of reproducible experimental evidence undermines the hypothesis. Critics argue that observed anomalies are better explained by contamination or experimental error. A major critique of water memory studies is the lack of consistent controls. Slight differences in experimental conditions, such as temperature or pH, can lead to significant changes in water's behavior, complicating interpretations of results. Attempts to reproduce water memory effects under double-blind conditions often fail, suggesting that initial observations may have been biased. Dismissing water memory is like debunking a magic trick by revealing the magician's hidden tools. Future research into water memory may involve more precise techniques, such as ultrafast spectroscopy, to observe molecular dynamics in real time. Machine learning could be used to identify patterns in experimental data, providing new insights into water's complex behavior. Understanding water memory, if it exists, could open new frontiers in nanotechnology, biology, and medicine. Quantum simulations of water's behavior at the molecular level could help clarify whether memory effects are feasible within the constraints of known physics. Collaborative research across disciplines, including chemistry, physics, and biology, is essential to resolve the debate. A recent proposal involves studying water under extreme conditions, such as high pressures or confined in nanoscopic spaces, to investigate its memory-like properties. Researching water memory is like decoding a language written in disappearing ink. It requires cutting-edge tools and collaborative effort. Water memory remains a controversial topic at the intersection of science and pseudoscience. While its proponents highlight intriguing anomalies, skeptics emphasize the need for rigorous, reproducible evidence. Resolving this debate requires overcoming technical challenges, addressing experimental inconsistencies, and adhering to the highest standards of scientific inquiry. The broader significance of water memory lies in its potential to challenge and expand our understanding of molecular interactions. Even if disproven, the research could yield valuable insights into water's unique properties and its role in life processes. Ongoing investigations into water's anomalous behaviors may eventually clarify whether memory effects are real or a misinterpretation of experimental results. The scientific dilemma of water memory is like a puzzle with missing pieces. Solving it could either reveal a groundbreaking truth or confirm a long-standing illusion.